being recorded.
Yeah, welcome everyone to this latest Orion Hangout. It's been a while, and it almost feels like the most recent Orion Hangouts and our meeting in Leiden happened something like 1984 or so, some long time ago. So it's great to see that there was a lot of interest in keeping up with the Orion Hangouts now on Zoom, and it's good to see also that few of you were over Zoomed enough to actually no longer be interested in joining other Zoom calls and talks. And we are actually restarting not just with one presentation, but we are getting 3 talks for the price of 1 today for the our Orion Hangout, with a nicely interconnected set of talks that I'm really looking forward to on the Orion B project. The way we will do this is we will have 3 talks of 15 minutes each, and then we will have time for discussion. And I would actually say, in order to get organized for the discussion, we can actually collect questions on the chat. And then as we go into the full discussion after the talks have concluded, you can then also unmute yourselves, and we can go over the questions more or less in order of what we have in the chat. Yeah, and so thanks to Jérôme, Émeric, and Pierre for volunteering to give these talks. Really looking forward to seeing them. And with that, I think we can get started.
Thank you, Jan. So today, Émeric, Jérôme, and myself will be talking on behalf of the Orion B consortium about millimeter rotation lines as diagnostics of the physical condition inside the giant molecular cloud in the case of Orion B. So I'll start just with one slide with a brief reminder of what is Orion B. So Orion B is a map of a large program IRAM 30 meter of 5 square degree to map most of the Orion B cloud at 26 arcsecond resolution. And in spectra, it's the full 3 millimeter band at 200 kilohertz resolution with a noise of 0.1 to 0.5 Kelvin. The main science goals are to elucidate the link between star formation and the structure of the host parent cloud, studying dynamics, physics, and chemistry, and also to build an unbiased data set with tracers of all the components of the cloud. So it's a huge data set, and we regard to develop new tools to explore first high-dimensional data and then to understand the star formation as a statistical question using modern statistical, in particular machine learning tools. So one important point in this consortium is that the collaboration between data scientists and astronomers. So we published many papers, and half of them are led by statisticians working with us to develop new methods to apply to this large data set, which are becoming more common with new instruments. So the first third of the talk, I'll be talking about tracing the amount of gas along the line of sight on the sky. So we all know that direct observation of cold H2 is impossible, so we need to use detectable emission from other trace methods. The first one that is often used is far infrared thermal emission of dust grains, but this requires a space telescope. Last one we had was Herschel. Other well-known tracer is using, for example, CO and CO conversion factor, the famous XCO. Using a molecular tracer is interesting because some molecules are observable from the ground, so we can have high angular observations. And one of the difficulties is that the relationship between the intensity and the amount of gas can be nonlinear. So you see an example here at the bottom of the screen at the scale of whole GMCs. When you look at the local group, you see that there's a linear relationship between the CO luminosity and the virial mass here. But once you get into smaller scales, for example, the scale of Orion B here, where we resolve the emission, we see immediately that there are non-linearities that appear. So the question is, can we do better than using a single molecule? And can we do better using many lines? So in a paper in 2017 in the Orion B consortium, we showed with a principal component analysis method that indeed, when you decompose the emission of the molecular lines, you see that there's a linear combination of the molecular line after you apply a transformation, but there's a linear combination of lines that is well correlated with the column density. Well, this was not new information, but the next step was going from this qualitative result to a quantitative result. And for that, we go into the range of regression method. And the idea is to use a machine learning method to predict a quantity. So here the quantity we're going to predict is NH2. In fact, it's the Good Belt Survey Herschel map. So it has all the potential biases of the column density from the dust, but this is what we're going to try and predict. And the observable that we are going to use are the integrated intensity and peak temperature maps for 18 molecular transitions that we had on the full map. You see here the range that we have observed. So when you do regression and machine learning, you need a training set and you need a validation data set that has never been seen by the method against which you can compare the result. So in our case, we validate our result on the Horsehead pillar, which is here, a region we know well, we've observed extensively. And we train on the complement, the whole part here that you see on the left. So this is a general tool for all regression method. In particular, we use the random forest, which is a non-linear regressor, which is going to be able to have a compromise between high flexibility and interpretability. So it's not as far as a neural network, which are difficult to interpret, but it's still flexible enough to get a really good result. So you can read about random forest in this paper, but basically it's a combination of decision trees, so piecewise fit by constant values, but you take a lot of them and you average the results out at the end to get less biased results, and especially less sensitivity to noise. So let's dig into the results directly. So this is a figure that shows the comparison between different methods by line. The first line is the XCO method, where we just multiply the CO intensity by a constant XCO factor. A linear method combining checking which are the best linear coefficients to get the regression, and the random forest method. And in the different column, the observed is the Herschel map. Predicted is our regression prediction. And here is the ratio, logarithm, of the two maps. So you see immediately that XCO is strongly, has large errors. And as you go into a more flexible method until the random forest method, you get more and more precise results. Another way of looking at these results is to trace the histograms of the residual maps that I've shown you before. So here you have the 1D histograms on the right, and 2D histograms comparing the observed Herschel maps to the predicted values that we give. And we can compare different methods. So the XCO method is not too bad for column densities above 10 to the 510 to the 21, or around that, but it's really bad below, because probably CO is not a good tracer of these regions. And you see here, it appears that a large bias on the prediction. If you use a multivariate linear regression, then things are a bit better, but still you see that the histogram of the residual is double peaked and it's quite large. And you see that indeed the biases are biased high. The prediction is biased high for low column densities and biased low for intermediate column densities. And showing the random forest regression now, the residuals are normal. The bias is very small. The variance is the lowest of the different methods that we used. And indeed, when you look here at the distribution of the residual maps, indeed it's quite unbiased along and narrow along the full range of column densities that we can predict. So the conclusion is that we can predict up to about 20% RMS from these 18 lines, the column densities of H2. Now, since we chose a method that we chose it to be interpretable, so what we can do is what is the evolution of the prediction when you add lines? So here is the prediction using only 13CO. The second column is the prediction using 13CO and 12CO. And you see that when you increase the lines, you add more lines, you get more and more precise reconstruction, and you get a reconstruction that become precise at different regions, at different places in the map. So one way of studying this effect, so if you look at what are the 4 key species to, on average, reconstruct the column densities, is 12CO, 13CO, C18O, and 8CO plus. You see here the decrease of the RMS as a function of the number of lines, and then it becomes you've done most of the work with the four first lines. But what we can do is use a decision path for each pixel of the map to study the contribution of each line to the column density and study it as a map to understand where the contribution comes from. So these are maps of the offset from the average data set in NH2 for different molecules. You see here that 13CO contribute mostly and around the test set that has not been seen by the method. So you see here that 13CO contributes mostly from the Horsehead Nebula, the Horsehead Pillar. 12CO is interesting because it contributes to the edge of the pillar. So it's probably because here in the neck of the Horsehead, it doesn't contribute because it's probably very optically thick. So it won't contribute to the column density, but in regions where it becomes thinner, it starts to have a contribution at the edge. 18CO is a very good tracer of the densest part of the pillar here. And HCO plus is a good tracer of the UV illuminated region. You see its contribution is almost nil everywhere, except on the UV illuminated sections of the Horsehead Nebula. Another way of looking at these contribution maps is to look as a function of the column density. So here you have the offset in contribution of each line to the column density as a function of the column density, here expressed in magnitudes. And here it's been divided into 4 columns. At the left here, you see the contribution, the lines that contribute to lower AVs from 1 to a few. So this is the contribution to the most diffuse gas. You get lines which have contributions below about between 6 and 10, so intermediate translucent gas. And then you get contribution to AVs that are higher than 10, so C18O, HNC. And then finally, you see that even though on average you only need the 5 lines, 13CO, 12CO, HCO plus, C18O, to reconstruct the column density, in some regions, especially for high AV, you need some specific tracers, for example, N2H+, which are very good tracers of the most dense regions of the interstellar medium. So in summary of this first part, the column density can be inferred within a typical factor of 1.2 from the Herschel-based column density estimates. On average, the lines that are most important, the 4 lines which are most important are the COI isotopologues plus HCO plus. But the importance depends on the regime, if it's diffuse, translucent, or dense core conditions. And in dense core condition, N2H plus is important. We've tried to infer FUV illumination or dust temperature. It's more difficult to infer, and we are now working on using a neural network regression to reconstruct the dust temperature and FUV illumination. It seems to be working on our first results. And now I let Jérôme speak for the next part of the presentation.
I will share my screen.
Yes, I stop sharing and you can share.
So, do you hear me?
Yes.
Sorry. I'm stuck. Okay. So once we've seen that it's possible to get an estimate of the column density from molecular lines, the question is why. So Pierre have shown that the CO isotopologues play a great role in this determination of the column density. So this is one reason why we first focused on CO isotopologues. The other one is that CO isotopologues are known to be a probe of elemental abundance of carbon and oxygen in mostly in nearby galaxies, and the idea is to monitor the progress of stellar nucleosynthesis. So in order to try to understand, we need to do first radiative transfer. And so we try to do local thermal equilibrium radiative transfer model. And this is relatively correct because the typical density of a GMC is between 500 and 1000 H2 molecule per cubic centimeter. And the critical density of CO is of a few thousand particles. And the second thing is that we will try to do this analysis using a new robust statistical tool to take into account the fact that there is limited signal-to-noise ratio in the observation. So how are we doing this? So first, we need to start with a physical model. So I've just told you that it will be a radiative transfer. The intensity as a function of physical parameters, theta I, who are the excitation temperature, the CO column densities, the centroid velocity along the line of sight, and the velocity dispersions. Okay, so it's not exactly the full width attack maximum because there is widening by the opacity that is taken into account in local dynamical equilibrium. And the second thing we will use is a noise model, and we will assume that we have additive white Gaussian noise of typical RMS sigma. So Fisher have shown that if you have one given physical model and one noise model, you are able to quantify the amount of information that can be extracted from the data completely independently of the methods you will use to extract those data. So how did it show this? How do we do this? We are computing first the Fisher matrix, which is related to the model by the derivative of the intensity modeled as a function of the physical parameters. And the noise level is taken into account in this matrix by the RMS of the noise. So those are partial derivative of as a function of theta y and theta g. So you have a bidimensional matrix that you invert to get f minus 1. And if you're taking the diagonal terms, for instance, EII, you will get what is called the Kramer-Rao bond for the parameter theta y. So what is this bond? It can be shown that this bond is the best precision that is achievable for this parameter. So more precisely, it means that this will be a lower bound of the variance for any unbiased estimator of the parameters. So why is this important? It's because if you have an estimator, for instance, a maximum likelihood estimator, You compute the CRB for your model and the data, and you are able to have a comparison of the precision you obtain compared to your derivation. So if the error bar of your derivation is of the same order of magnitude of the Kramer-Rao bond, this means that within this model, this physical model, you won't be able to extract any more information. So how can we use this? So here I'm showing first the square root of the Kramer-Rao bond for the logarithms of the column density. For the three images, that's what is shown as a function of the excitation temperature and the column density. So this is just modeling, simulations. So these strange bits, in fact, give us the relative precision you can get on the column density. So a value, for instance, a value of 0.1 will mean that you have 10% precision on the column density. A value of 0.3 means that you will get a precision of a factor of 2 for the column density, and a value of 1 means that you have a precision of factor 10. So, of course, we want a precision that is better than factor 2, at least. And so here we are putting in brown and green those regions. So why I'm showing three different images is because in the first image, I'm showing the precision we can get when you're interpreting one rotational transition alone, the 13 CO G equal 1 to 0 transition. Now, if you're analyzing the 13 CO G equal 2 to 1 transitions, you get something that is different in details, but similar qualitatively. Now, the big difference happens when you're trying to analyze, to invert both lines together. You see that the regions where you can get precision that is better than a factor 2 is much larger than in the parameter space than before. And you see that in regions where where you can't get a good precision, the precision is still improved by a few order of magnitudes. So this is not a new result, the fact that it's better to have several transitions to have a better derivation of the column density. But the nice thing now is that we have a quantitative way to estimate the improvement in the precision. The second application is to try to apply this to the interpretation of CO isotopologues. So I've just shown that having two rotational lines is much better than having one line. And unfortunately, in the Orion B project, we have only did only 3 millimeter band. So the C180120, C13CO120, and 12CO120 are coming from the Orion B project. But we were fortunate that Nicolas Peretto had ancient 30-meter data for the C180221 and 13CO221 on a subset of the fields that get the Orsted and NGC 2023 regions. And so we were able to analyze all of this. And the idea is to try to understand why with CO, you can trace different regimes of column densities. So we just use a maximum likelihood estimator that we show that is unbiased and efficient in the parameter space we will use. In the next slides, we will filter out all the pixels that have Kramer-Rao bonds that is much too large, and for which it means that we can't extract any information useful. So first, I'm showing the excitation temperature of 12 CO as a function of 13 CO, and the excitation temperature of 13 CO and C18O. So you see that while the excitation of temperature of C18O and 13CO is centered on a line of slope 1, so typically within a factor of 2. It's not at all the case for the excitation temperature of 12CO compared to 13CO. Here, it's more centered on a line of slope 2 with a factor of 4 between for all the values. And that's not just noise. You see that you have a very well-behaved map of, very well-behaved maps of excitation temperature. So we can be confident in our derivations. So why is this important? It's because if you assume the same excitation temperature for all CO isotopologues, you will bias the estimation of your column densities. So here, that's not what we do. And in fact, we can get accurate estimation of column densities of 12CO, 13CO, and C18O, and thus relative abundances. So you see that for the column density of 12CO versus 13CO, the abundance between the two spaces is between 10 and 60. So 60 would be the value that you would get from the elemental abundance of carbon, 12 carbon versus 13 carbon. And but you have a relatively large dispersion of value, and this is understood in terms of chemical fractionations. Okay, the fact that 12CO can recombine with 13C plus to give 13CO plus 12C+. Okay, and so you have an enrichment of 13CO. And for C18O, the abundance ratio should be 8 if you're just looking at elemental abundance of carbon and oxygen. And in fact, you have a value up to 40 or so. And in fact, here, this is due to selective photodissociation of C18O and depletion on ice grains that is more important for 13CO. Now, if you're looking at the typical value of the abundance of 12CO, 13CO, and C18O, we get typical value that we find in other GMCs in other studies. So we don't think we're biased. Okay, so to conclude, we think that the Kramer-Rao bond is a powerful statistical tool. It has been used in other areas of astronomy, but not so much in ESM studies up to now. Of course, fitting two different rotational lines of CO can improve the estimate of the column density by a fair amount. It's important to take into account when you're using ETL, it's important to take into account that different CO isotopologues have distinct excitation temperature, else you will bias your column density, the derived column density. We find things that are consistent with the previous determination, and but there are significant local deviations compared to those mean values, not only in exposed UV radiation field, but also in UV shielded regions. One result that I didn't show is the fact that we also measured the velocity dispersion, and we see that C18O are produced in less turbulent regions than 13CO. It's a 10% effect, and we can show with the CRB that it's a significant effect. So the next steps will be to try to use more complex radiative transfers methods like LVG, for which we hope to have to be able to constrain the density and the temperature, the kinetic temperature. Thank you.
Okay, and I will share my screen for the last part. Up. Okay, so Jérôme, do you all hear me and do you all see my slides?
Yes.
Okay, so Jérôme has talked about the statistical subtleties of trying to estimate physical parameters from the observation. Here, in this last part of our presentation, I'll talk about the estimation of another physical parameter, a very important one, the ionization fraction of the gas in the GMC of Orion B, which presents a slightly different kind of problem. So as you probably know, the ionization fraction plays a key role in the physics and the chemistry of the neutral ISM. First, because it allows fast ion neutrals reactions, which will enable the development of interstellar chemistry in molecular clouds. Second, because it's controlling the coupling of the gas to the magnetic field, which will have important dynamical effects, especially during the collapse of prestellar cores. It also affects the efficiency of the photoelectric heating mechanism, one of the most important heating mechanisms in the ISM, because the charge state of the grains depend on the ionization fraction in the gas. And finally, it can also affect the excitation of high dipole moments molecules, such as HCN, because of collisions with electrons, so that the interpretation that we make from the observation of those lines actually depend on the assumption we make on the ionization fraction. So in molecular clouds, the ionization fraction will vary by several orders of magnitudes. If you are in star-forming regions with very young, massive, and bright stars, close to them, you will have an ionized region where everything is ionized, so the ionization fraction is 1. Then, as you've passed the ionization front, hydrogen becomes atomic, neutral, but there are still UV photons able to ionize carbon, which will provide an ionization fraction of around 10 to the minus 4. And then, as UV photons are extinguished, the ionization fraction will decrease until you reach very low values that are maintained by ionization by cosmic rays in the cold, dense core parts of the cloud. And where observations have shown that you have values between 10 to the minus 6 and 10 to the minus 9. So now the question is, how can we estimate this physical parameter in our observation of a GMC? The classical methods use deuteration ratios for molecules, and especially the deuteration ratio of HCO+, so DCO+ over HCO+, based on the idea that this ratio traces the H2D+ over H3+, because deuterium enters the chemistry of complex molecule through the deuteration of H3+. And this ratio is controlled by enrichment at low temperature, so this reaction, but this enrichment will be limited by electronic recombination. And so the deuteration ratios of molecules, and especially of DCO+ over HCO+, should be sensitive to electronic abundances. So what I show here is the expected relationship proposed by Caselli et al. In 98 of the ionization fraction versus this DCO+ over HCO+ ratio. We see already that one limitation is that it's dependent on the depletion in the gas. If I overplot here some more recent astrochemical models, so of course the chemical rates have changed a bit, but qualitatively the situation is still the same. We see that actually the main origin of the large scatter that we have here comes not from the depletion factor, but actually from the H2-ortho-to-power ratio, which is itself a very difficult parameter to estimate observationally. And the third limitation is that in this region, the slope of the relationship between the ionization fraction and the DCO+ over HCO+ ratio is extremely steep, meaning that a small observational uncertainty on the ratio will result in a very large uncertainty on the estimated ionization fraction. But before all those limitations, in our case, there is one even stronger problem, which is simply that if we look, so this is only the first square degrees of our Orion B observations. If we look at the detection masks of DCO+, we see that we only detect DCO+ in the densest cores, and this represents only an extremely small fraction of the surface of the maps that is observed. So if we want to have an exhaustive view of the ionization fraction in a GMC, including in the more diffuse envelope of the cloud, we need to find new tracers for tracing the ionization fraction. So now the classical, and of course we want to do this based on astrochemical models. So the classical way to use astrochemical models in conjunction with observations is that we have observations, line intensities, for instance. We compare them to models, which gives us the region of the parameter space of the model which agree with the observations, and doing so, we can determine the physical parameters of the model at the different positions of the map. The problem with this approach is that if the lines that we have observed do not provide enough information, are not constraining enough for the parameters that we want to estimate, then the estimation that we will get will be badly constrained and degenerate, and we won't be able to use it. So here we choose to adopt an opposite approach, where we start from a grid of models which predict both all the potentially observable quantities and the variables of interest, here the ionization fraction. Based on this, we want to find what are the best tracers of a given physical parameter. So here's the ionization fraction. And then based on this, we will be able to plan new observations or exploit existing ones. So the idea for doing this is to say that we know that there must be a relationship between the observable quantities and the target physical parameter. But this relationship is affected by other unobservable parameters, for instance, the density, the gas temperature, the UV field, and so on. And so the idea is to treat this, the effect of those unobserved parameters as a source of noise, of uncertainties. And so in the relationship between any observable tracer and the ionization fraction, this unobserved parameter will cause some scatter in the relationship, and we will try to find the observational tracers for which this scatter is the smallest. So here, in order to introduce the minimum amount of a priori information, when we sample over the unobserved parameter, we sample with a uniform distribution with simply minimum and maximum bounds corresponding to the realistic range of values. And then what we will need is first an astrochemical model to produce a data set that contains both the observables and the target variable. And then based on this data set, a way to estimate the predictive power of each of the potential observable. So let's start first with the model. We use a stationary chemical model with a rather complete chemical network, gas phase chemical network with 300 species and almost 10,000 reactions. And we explore a range of values for a large number of input physical parameters, the gas density, the gas temperature, the external UV field, the shielding of the gas, the cosmic ray flux, the H2 ortho to power ratio, and so on. And because we expect that the best tracers will probably not be the same in very different types of mediums, we actually did the study on two different grids, one exploring ranges of values typical of translucent gas, and the other exploring ranges of value for dense gas. And in particular, in dense gas, we also include the effect of a depletion factor. And then we choose a list of potential observables. And what we will consider here as observable will be only ratios, either abundance ratios or column density ratios, or line intensity ratios, where the line intensities have been computed with post-processing of those models with RADEX. And so we construct all the possible line ratios or column density ratios, and now we want to find which are the best tracers of the ionization fraction. So the way we do this, the idea to evaluate the predictive power of any given tracer is that we train a machine learning regression model on the task of predicting the target quantity, so the ionization fraction based on that observable tracer, based on the model grid, of course, and with the idea that if we manage to reach the best possible regression model, it will capture all the available information about the target that's contained in this tracer. And so a measure of the goodness of fit of this regression model, for instance, here the R-squared coefficient, will provide a measure of the predictive power of the tracer. And here for our machine learning regression model, exactly as in Pierre's paper, we use random forest because they provide a rather flexible model, so that will be able to reach a maybe not the optimal regression model, but pretty close to the optimal regression model, and at the same time is sufficiently lightweight so that we can train it fast on a moderate size dataset. So let's move to the results. So we applied this. Let's first talk about translucent medium conditions. So what I show here is the goodness of fit measure, the R squared, which goes from 0 to 1 for all the possible tracers ranked by their predictive powers. So the R squared goes from 0 to 1, with 1 being a perfect prediction, and this number representing the fraction of the variance in the data in the model grid that's explained by a given tracer. So we see that we have actually a lot of very good tracers, which explain around 90% of the variance in the data. And if we look here for the first one, which is C2H over HCN, the line ratio, we see that we indeed have a very good, a very tight relationship between the ionization fraction and this line ratio, with a scatter which is relatively small. And so this line ratio should allow a pretty good estimation of the ionization fraction. We see that in this case, most of the ratios that we find involve C2H. And this is understandable because C2H has been observationally related to the UV field. And actually, that's because the formation of C2H is initiated from C+, and also involves recombination reaction. So it will be most present in regions where the ionization fraction is high and UV photons are still present. Now, in the cold dense medium, I show here the same kind of plot, but this time for cold dense medium conditions, we see that we still have pretty good tracers, a bit less good than the previous case, but we still have pretty good, pretty tight correlation relationship with a slightly larger scatter, but we will still be able to estimate at least the order of magnitude of the ionization fraction. And the interesting point here, so we see that several of the ratios involve DCO plus or N2H plus. DCO plus we have seen in the introductions why it was related to the ionization fraction, and N2H plus will also be related as the ionization fraction will control the abundance of molecular ions in cold dense clouds. And the interesting point here in particular is that we see that we managed to find relatively tight relationship, despite the fact that in our model grid, we vary several key physical parameters by order of magnitudes, meaning that those relationships are really caused by physical or chemical reason. And in this case, for the 13CO over HCO plus line ratio, the reason is actually not chemical, but physical, simply because in those cold dense medium conditions, this tracer actually traces the density of the gas. And we found in our models that the ionization fraction is very strongly correlated to the gas density in cold dense medium conditions. And finally, because random forest, so we can use random forest directly once we have observations to estimate the ionization fraction, the random forest models that we have trained, but those are a bit complicated to provide to observers so that they can easily use them, because they will be based on library-dependent file format, which might change over time. So we also provide simpler analytical fits that can be provided as a coefficient table, so much easier to use. And we as well did an analytical fit of the scatter of the data points around this relation, so that observers can estimate not only the ionization fraction, but also the uncertainty on this estimation of the ionization fraction. So to conclude, the first point I want to emphasize is that the method that I have presented here is completely general. It could be applicable to any model type, PDR models, time-dependent chemical models, and it could be applied to find predictors of any unobservable physical variable. So, for instance, density, depletion, the cosmic ray ionization rate. And so we provide the code for this tool at this web page. The second conclusion is that we see that in both cold dense medium conditions and translucent conditions, we do find several good tracers of the ionization fraction, and we are now in the process of applying this to our observational dataset. And of course, the natural next step would be to move beyond the simple stationary chemical models that were that had no spatial profile that were used here, and to move to more complex models, for instance, including the spatial structure along the spatial gradients using PDR models, including surface chemistry and so on. And that concludes my talk. Thank you.
Excellent. Yeah, thanks a lot for these 3 very exciting talks. At this point, I will actually stop the recording for the discussion.